So I'm Sean Carroll of Caltech, and my fellow panelists here are both professors at UC Berkeley. Yasunori Nomura is joining us, and Rafael Busso, who's already given a talk. And our job is to talk a little bit about the role of the observer in cosmology. So I wanted to start by something that Rafael said, a provocative thing at the beginning of his talk, that as soon as you hear the idea of the observer in physics, your first response is to say, no, we shouldn't talk about the role of the observer in physics. The good physics is the physics that doesn't have observers mentioned in it. So that used to be, perhaps, the point of view. Could you sort of fill in, if we were citizens or students in Isaac Newton's day, how that would have been the perspective we had?
Right, in Isaac Newton's day, we had a very simple picture compared to today, I think, of the universe, in which, first of all, there was a clear separation between space and time. You could state the position of all the particles and cannonballs and whatever you wanted to compute at one time. And from that, you could predict where everything was going to be at any other time. And that was going to be true whether or not somebody observed it. You never had to worry about anybody going in there and making this or that measurement, and depending on that, you see a particle or a wave or all this confusing stuff. And I think what happened is that, you know, as we moved into modern physics at the beginning of the 20th century, both that space-time picture changed, and suddenly it became kind of confusing because there are limitations to what one observer can even see. There's only so many places from which light could have reached us. And so not everything can actually be checked. Maybe that's important. And on the other hand, quantum mechanics seem to tell us confusing stuff like the observer is actually important to have some kind of definite outcome or definite state, like whether a cat is alive or dead. And I think, well, from my perspective, that led to an important re-examination of the role of the observer in physics, though it probably initially also led to an overreaction and some sort of excess mystery that was introduced into the problem.
Right. So in some sense, maybe Yasunori, correct me if I'm wrong, one way of saying it might be in Newtonian mechanics, classical mechanics, every observer should be able to say exactly the same thing about anything that is going on in the universe, and therefore the idea of an observer isn't that important.
Yeah, the idea of observer not being important might be slightly strong in the modern world of quantum mechanics, because physics is supposed to predict what we will observe. Okay? There is somebody who make a measurement, then what we observe. And the observers, the word observers is often used in a confusing two different ways. One is about reference frame, like things to describe physical system. Even in a Galilean time, if you change observer and we go to the system, which is moving with a constant speed with respect to the other reference frame, then description changes.
Maybe explain what Galilean time is.
That's like a velocity of some object is, say, 50 miles per hour. But if you are moving, yourself are moving 20 miles per hour, then that object looks like moving at the speed of 30 miles per hour. Okay? So like the description, namely velocity changes. That doesn't have any meaning, same meaning for everybody.
Right.
Okay? And the extreme form of that we start to learning is in quantum gravity. What is called space-time and so on depends on the reference frame we use. We may later discuss, like, if you're observing black hole from exterior, process looks like certain way. If you're falling in black hole, process looks completely different way. And there are some new region of space-time may show up, some all the space-time region may disappear. Those things might happen.
So you guys are great because no matter what question I ask, you end up talking about quantum gravity, which is good. That's a good thing to talk about. But still, let's bring it back a little bit. I want to know, like, there was this transition already mentioned just from Newtonian space and time, which is the same as Galilean space and time, right, to relativity, right? And is it fair to say that when we got relativity in the game, the notion of the observer became a little bit more crucial to how we talk about physics?
But I'm saying that when you say observer in that context, that's the frame of describing physics or way to describe physics.
The reference frame.
That's very different from physical observer. Right. You're observing and you have, say, consciousness, if you want to say it, and you have some information processing and then how that will affect. Those things does not depend, if you ask the right question, it does not depend on what kind of description you will choose. You simply have a map between certain description and certain other description. Those different description, quite often people say observer, but that's not about the physical observer actually doing some measurement and making information processing. And think about it.
So this is a good point. So in some sense, in relativity, it didn't really promote the observer that much in both before and after, I guess. So one way of saying it would be when Newton was there, we all thought that everyone agreed on the length of a meter stick. And then when Einstein came along, well, maybe we didn't agree because they were moving at different speeds. But as you say, even before Einstein came along, we didn't agree on how fast the car was moving,
Exactly,
right?
exactly.
So it's just that there are still things we agree on, but the set of things we agree on differs from Newtonian mechanics to relativism.
That's it. And then, but the quantum mechanics really changes, apparently.
Quantum mechanics
so
is very
really required for us to think about what the physical observer is, what the measurement is, when you can define even those questions, which you can.
All right, but I'm not going to let you get away with giving up on classical physics so far. I mean, Raphael, tell us a little bit about this idea of you're not able to see the whole universe, right? We have the speed of light is now a new limit, and that really does give the observer maybe a bit more oomph in relativity than it did in Newtonian mechanics.
Well, I think we have to distinguish between different kinds of relativity. So when we took that step from the Newtonian space-time picture to special relativity, I would agree that that wasn't such a radical shift in terms of the role of the observer. I mean, in particular, what changed are only the invariants were different. So before that, everybody could agree on how much time elapsed, and everybody could agree on the spatial distance at a fixed time. And after that, it was some combination of those two things that everybody could agree on, but they could still agree on it. And you know, that's still true in Einstein's second theory of relativity, general theory of relativity, which he invented to describe gravity. But there's a new element that brings in, which is that space and time themselves become dynamical. They can have a beginning, they can have an end. And that's not present yet in his special theory. That came 10 years later. And at that point, you start having observers which are inequivalent, even if you wait for a very long time. So in special relativity, you could have two observers that at a given time have access to different information because they live far apart, and light from some supernova explosion has reached one of them, but not yet the other. Okay, so if they wait a little longer, they'll both see that thing, and then they'll agree again, they'll all be happy, right? But in general relativity, it's possible for one of these observers to fall into a black hole and die a horrible death before that information ever reaches that observer, and space and time are just over, at least as far as that theory tells us. And so now there's a real inequivalence there between those two observers. They have totally different histories that never become completely reconcilable. And
so in special relativity, if you wait long enough, everybody shares the same universe. Even in general relativity, even that, no matter how long you wait.
That goes out of the window, and that seems to be important. I think that, well, there are some arguments that we even get into contradictions, internal contradictions in physics, when we don't take this fact into account and pretend that there exists a kind of super observer who gets to see everything.
So falling into a black hole is an obvious case of that, but cosmology is also another case, right?
Yeah, to some extent, like description of interior black hole is kind of related with the cosmology. We usually have, in the following sense.
All right, so explain what both those are individually, and then tell us why they're the same.
I'm not saying, of course, interior black hole is a cosmological spacetime. It's probably not, but it's in certain sense the problem is common. That's what I mean. Usually in particle physics and so on, we describe. You necessarily have to go to quantum mechanics. You may want to stay in classical mechanics.
I'll let you talk about it. It's okay.
Yeah,
I'll let you do it.
Yeah, because the minute you really talk about observer, you can't really avoid quantum mechanics. And in usual quantum mechanical problem, say in particle physics, how we describe the process is like you're sending in some particle and interact and then collide, big collider, and then go out. And you describe if you initially prepare something and then what you will see at the end.
So like at the Large Hadron Collider, smash some protons together,
exactly.
watch what comes out.
Yeah. But to describe in those ways the physical process, you're implicitly assuming that there is something you prepare these states or these particles and then observe later. And you can assume this because you're talking about some small region or some subset of the system, so you can really assume implicitly there is some super observer and so on. But cosmology, if you mean by cosmology, may depends on person, but to describe everything, whatever that means. Okay?
The whole universe.
The whole universe or everything, whatever that means, including those people who prepare this particle and observing later, then you can't do this. Okay? So you really have to, you cannot
You
say,
can't
do describing just like the way particle physics describe these processes. So
you can't just wait until all the dust settles and
yeah, you just really have to include like all these things. What's a measurement? What you mean by
because the world is full of stuff, and the stuff is bumping into each other and interacting and entangling and all that.
Exactly, and then also you cannot say that this is an infinite, or at least this is assuming infinite system. If it's an infinite system, you can implicitly separate part of the infinite to be observer, whatever, preparing the particle and observing later. Part of the infinity to be described by this process of scattering or something. But if it's a whole system is, for example, suppose it's finite, we don't know, maybe infinite, but if it's a finite, then you can't do this separation. At least you can do only approximately. You really have to talk about what the observation means in that case. You really can't avoid it. It may be much more conservative than we may imagine now, like the answer may be conservative, but we cannot avoid talking about it. That's because of quantum mechanical.
Okay, so this is a statement about cosmology.
Yes, cosmology.
So
in
far,
cosmology, you have to do it.
and our inability to describe the evolution of the whole universe in the same way that we describe a little particle physics experiment. How does that match up to the black holes?
Okay, so in that case, if you're falling into black hole, you don't have obvious region of, say, something we often call asymptotic region. If you're staying outside the black hole, you can prepare something, and you send in something in the black hole. The black hole may evaporate later through so-called Hawking radiation. You may,
evaporate, yeah.
yes, and then you may collect those radiation at the infinity where you're staying. So you can have this description, you're staying in infinity, or you infinity far away, you observe what's happening in black hole, and later you observe again. But now if you jump into black hole, you're already inside. You cannot wait infinite time and staying outside. You really have to
die a horrible death.
yes, exactly. As Raphael said, it's just something dramatic happens.
Finite number of years left.
Probably finite number, maybe finite space-time, and so at least naively it's like that. That situation is a little bit common to cosmology. Then you really have to think about system infinite. You cannot resort to some infinite, the big, infinitely far away super hyper observer. So in that sense, it's a similar thing.
So matching up with what Raphael said, once we have general relativity, whether it's cosmology or a black hole, there's a sense in which you can't just wait for all the dust to settle and then say what happened. You have to sort of work there in the messy gear wheels and see what's happening at every moment.
You have to define everything in that inside the messy thing.
And even at sort of a more low-tech level, isn't it true, Raphael, that we know the universe is accelerating, and that puts a limit on how much we can see in the universe? How much an observer can see, to match the lingo that we're trying to use here?
Right. So we could have hoped, right, that the universe becomes infinitely large as we wait for it to expand more, particles get more diluted, and we could have tried to be careful and not fall into a black hole, not die a horrible death, which is what happens.
Horrible death, right. Bad idea.
And maybe, after a while, it would have even turned out that this universe that seems to be sort of filled to infinity with particles that are just expanding away from each other, or galaxies, maybe there's even an end to it, and it's finite. If you just wait long enough, you see that we're just part of an expanding ball of stuff. And you could have hoped to, recover a kind of situation that we're used to from a lab where we look from the outside in, where we can make our way out of that ball and look at it from the outside and think of it as at least the end result of some experiment that we maybe didn't set up, but we can measure it the way we always did and measure it perhaps very accurately. And there were already a number of subtle reasons why that seemed like it wasn't going to help very much, but that was just completely swiped off the table by the discovery that our universe is actually like a box, that we live in a box. It's a spherical box. The reason that it's a box is this acceleration that you just mentioned. So there's an accelerated way in which galaxies are moving away from each other. And what that means is that the light signals we're getting back from them can't keep up with how fast they're moving away from us.
That doesn't sound like we're in a box. So
It means that we're in a box because that means that there's a finite distance, which when they cross that distance, the light signals don't make it back to us. And so from our viewpoint, that's just like, they go black at that point when they hit the walls of this box. That's a few billion light years across
so
this
they don't
box.
hit the wall of the box.
Well, in some language, they just cross out of our horizon. right?
Just for our viewers at home,
but the
there's
viewers
not a
at
wall
home-
at the end of the universe
We
into
don't
which
know
you
that.
hit.
We don't really know that from our viewpoint, which is by far the most important.
Yes,
Um,
as far as we know.
it's
a
a
wall.
box, and you hit that box, and they get converted into thermal radiation that slowly arrives at us. So it's kind of
Alright.
similar to falling into a black hole. And at that point, it really gets hopeless trying to move out of the system and view it from the outside. Cosmology seems to throw a wrench into that.
Well, so it sounds very similar. Maybe this is worth emphasizing because maybe it's not a commonly talked about concept, but the way in which gravity, general relativity, the curvature and dynamics of space-time gives a little more oomph to the idea of the observer is this idea of a horizon, the idea of something separating what you can see and what you can't see. And this is common to both the black hole case and the cosmology case, right?
Yeah. Yes.
The fact that, I mean, the reason I insist on calling it a box is that this is the physics of the observer event, right?
Right.
If I was
Spherical.
willing to contemplate a super observer who can see all of the universe all at once, then yes, those galaxies are just moving sort of out of causal contact with us, but nothing special is happening. But if we're taking seriously the idea that an observer matters in cosmology, well, then these galaxies are really gone from the
Right.
description. Now, it's true that another observer will have a different story, but the point is those are the stories we need to be able to tell and not this sort of bird's eye view of all the universe at the same time.
Right. So these different stories, this is where the observer really becomes a necessary part of
Right.
our description. And quantum mechanics is going to play a big role there. But just to sort of nail it down, if we're probably familiar with the idea of a black hole, there's a region of space-time from which nothing can escape, there's a horizon around it. And what you're saying, Raphael, is in the accelerating universe, we're in the inside of this box, which is the horizon. We have a horizon, things can pass out of it, and then we'll never see them again.
Right. In both cases, a horizon just refers to a kind of boundary from beyond which nothing can get back to us. The more familiar situation is indeed a black hole where you throw something in, you keep getting light signals back, but at some point nothing comes back anymore and you can't scoop it out and it's just gone. It's behind the event horizon. Now in cosmology, we now know, this is relatively recent news, less than 20 years old, we now know that we're kind of like a black hole inside out. We're surrounded by a giant sphere, more than 10 billion light years across, that has the same property, that if you send your friend a little too far away and you want your friend to come back, that friend's not going to come back.
You're going to die
It's
of
just
loneliness.
like, yeah,
Not a
exactly.
horrible death, but-
He's good. That's right, out of loneliness. Or we will die out of loneliness.
And this would be interesting and cool, but perfectly well understood if it weren't for quantum mechanics. And quantum
Yeah.
mechanics plus this general relativity stuff makes things a bit murky. Is that
I
right?
think so, because this is, by the way, this horizon is really ultimate limitation of information and so on. The black hole case is really quantum mechanics already in it. If you compute something called entropy of the
Yes.
black hole or space-time, you're already hiddenly thinking about quantum mechanics, by the way.
Okay.
Otherwise, in classical world, if you just think about the black hole, you don't see the
Well, black holes have an entropy.
yeah, the people say that
And
means
it's a
that
quantum mechanical origin.
I think it's people know it, but it's quantum mechanical origin. So hiddenly you're already talking about quantum mechanics, to be honest. But if you're really thinking about the measurement, what the quantum observer or quantum measurement will give you, what kind of classical even space-time or classical result of a measurement you will get when you make a measurement. To discuss those, because those are the questions we want to answer. Physics want to answer, what physics wants to answer is really, if you make a measurement, what you will see. That
Those
is
the
a
only
question.
questions?
I think quantum mechanics is pretty much
Physicists
saying
don't
that.
want to know what's happening when we're not making measurements.
What's the meaning of that?
Well,
Raphael thinks he knows.
I think it's been a fruitful it's been a fruitful stance to take, that we try to ask questions about measurements that we can make, and we learn in the process of that by finding the right description of those measurements. We learn things about what measurements we could have made if our technology was good enough versus measurements we could never make. So the reason that it's safer to start with measurements we can make is that we know we're on safe ground and we can work outwards from there. If we start by thinking about how many angels are on a pinhead, then we're starting with a measurement we can't make, and we're doing meaningless stuff.
But by the way, I don't mean, of course, no, and I don't mean like a practical measurement, if it's a
Yeah, I
possible
know.
technical or something. In
I-
principle,
we're in
No
agreement.
one thinks
Yeah,
that we are
yeah,
talking about
yes,
practical
yes,
measurements. That was
yeah.
not a worry. But is there a danger that we get pushed to what is called idealism, in the sense that we think that what the job of science is not looking at an objectively existing world and identifying true features of it, but simply the world exists in our perceptions of it?
Oh, because quantum mechanics already doing to some extent that. That's my feeling. Quantum mechanics use something called Born rule. This is a rule or prescription to calculate the physical quantity in the framework of quantum mechanics.
Right.
That you will use that if you do some manipulation, literally called measurement, then what would be the answer to that? That's the part of the formulation of quantum mechanics already in a standard textbook formulation. Of course, we really have, probably that's only approximate the concept. We believe what is called Born rule, very specific prescription is probably only approximate. The real world is more called quantum many worlds and branching and so on. But the formulation already includes the piece called measurement as really crucial part for the definition of framework. So what the right, more complete quantum gravitational framework should reproduce that through the process of identifying what's the measurement.
Raphael, you were smiling.
Yeah, I really want to push back against what you just said, I think, only to get me to push back against
Exactly.
it.
Good. That someone could.
But the idea that you know, there are things that exist, that we have these preconceptions about what exists, and now we have to find a physical theory that works with that. That's been extremely detrimental to scientific progress. Having preconceptions is a bad idea. The way that we've made progress is when we do experiments and then try to explain them and see where that leads us. No philosopher in the whole universe would have ever dreamt up quantum mechanics. People would drag kicking and screaming to that. So on the one hand, by measuring boring spectra of atoms that I personally don't care about at all. But that's the kind of thing that leads you to revolutionary progress. Mm-hmm. And then you have to follow that to the bitter end, wherever it leads you. It's amazing, you know, what you can learn from that. You worry about Mercury going around the sun, and there's some tiny difference to Newton's theory of gravity that you can tease out of that by extremely painful, boring observations. Well, that turns out to be the key to checking general relativity, seeing that the correct theory is one in which space and time can bend, the universe is expanding, it might have had a beginning, it can end, there's a singularity inside a black hole. And so it's that connection between the hard-nosed, sort of boring, measure phenomena that intrinsically don't seem particularly exciting and measure them ridiculously well, and taking it from there, and then you get to the really exciting stuff about, oh my god, this is how the universe actually works.
Well, okay, but then that last sentence was fraught with peril. Is there the danger that if we emphasize instrumentalism in the sense of just explaining what we observe, we go all the way to saying that there is no such thing as an objectively existing physical reality? There only is a set of measurements that we make. And do you feel
But we get something else, right?
either way?
We get general relativity, which clearly describes how space and time behave. Okay, you can say it describes how all the experiments that we have since done to test how space and time behave. Right, but there's an intermediate structure, which is the theory, which uses certain mathematical language that turns out to be correct for describing all of those experiments and doesn't use certain other mathematical language that turns out to be incorrect. And it's out of that intermediary where we go from a bunch of observations and infer something general and then test that again with more observations, all of which are very specific and perhaps boring. It's that intermediate thing that we're after, and which gives us the sense that we are grasping some of the structure of how nature is put together. Whether that's real or not, I really don't care. So far, all of those things have been just better and better approximations. But as you get even Mercury right to the last, 10th digit after that little work in getting a little bit more accuracy comes with a complete revolution of how we think about space and time. Probably not the last one, but the fact that it does better at explaining all those experiments suggests that there's some truth to it.
But you don't care whether objective reality exists or not.
I have no idea what that question means. It seems entirely circular.
Disagree. I don't disagree.
This is very sad.
Disagree.
We need someone on here who's going to stand up for objective reality. I feel that,
Because
What's the difference?
Because I think that's what we're studying, isn't it?
Well,
That's
stand
the
up
point.
for it. Go ahead.
I'm purposely doing that.
Thank you very much.
We can get descriptions of our measurements, but if the descriptions of the measurements don't lead us to conclude at the end of the day, this has revealed something about the nature of reality, then why are we doing it?
Or about the measurement you made. Right? I mean, it's
All right.
objectively, you can compare a
So
measurement.
you grew
and
up
then-
when you were a little kid, you got very excited by the idea, someday I'm going to explain some measurement outcomes.
Yeah.
That was really
That's right.
I don't
That's
believe you.
right.
I think that you have convinced yourself after the fact that that's what you did, but I don't think that's what got you excited. I think you got excited because you heard there were things called black holes and quarks in the expanding universe, and the existence of these things got you excited.
Something you can potentially measure. In that sense. Of course, maybe practical, so that's why I just said really important to discriminate. Practically you can do it or something. Even if practically you cannot go there, you could say it's there.
Just went on the record that you don't need to throw away the existence of a true objectively existing reality to get all of the measurements to come out correct. You
As
might
long
not
as-
care, you're welcome to not care. But there's nothing in modern physics that says we're not allowed to talk about reality as it exists.
Let me throw you a bone, Sean.
Thank you. Thank you.
One thing you get out of this, right, is that you get to make measurements that blow your mind after you recognize how nature works from other measurements.
Right.
So, for example, you get to check that the sun really bends light rays. Maybe you get a kick out of that. You get to actually do quantum teleportation and send information without sending any physical matter. Maybe that gets you excited. To me, those are interesting applications. I'm more excited about the fact that all of those data that we have can be organized into such elegant structures at all, and the idea that more and more different phenomena can be organized into fewer and fewer fundamental equations and concepts. I can't tell you why I find that exciting, but I can't help it.
Okay, good. Well, maybe this actually does bring us back to where we need to be, which is let's be a little bit more clear about just quantum mechanics. Forget about, put aside quantum gravity, space-time, etc. We're going to bring that back to our space-time discussion, but what is it about quantum mechanics that makes observers and measurements something that require a little bit more chit-chat than they would have in the classical world?
I think as I also mentioned, even the current formulation is already doing it through something called Born rule and so on. Because quantum mechanics is essentially the framework to answer the question if I make a measurement and then what will happen from the beginning. Fortunately, or just the theory is formulated that way. The reason why we're talking about these observers and then why those might be the only things to make sense is not like because we want to think about that way. Because the formulation of theory required early on through Born rule, something called Born rule, to think that way. Of course, that Born rule itself will probably be approximation.
The Born rule is just the probability of getting a measurement
Yes.
outcome is the wave function.
Some description, yes, so for technical terminology. But so for example, in quantum mechanics, you can do some intrinsically quantum measurements, something called interfering the different probabilistic possibility you can interfere. Okay, those things are possible, whatever that means. Like you can prepare quantum mechanical two different probability in same space-time region even, and then interfere later, and you observe it. But what you observe is after converting those things to some experimental apparatus data, like some interference pattern on screen, that we can analyze using something called classical world, like Newton's world and so on. So it seems like anything you can really talk about literally is something already classicalized. Whatever that means, we don't completely understand yet.
Right.
So it seems like understanding that is a very important question. And the recent progress is that all these things are probably important to understand going back what's the space and what's time, because those concepts doesn't seem to be already classicalized one. Namely, you can talk about this position in space, this position in space, and that position in space, and this time. It may depending on the observer in a sense of reference frame. But the fact that we are already talking about those language, like space and time, seems to be already we're assuming this process of classicalization, what is in principle observable.
So
we're talking about
maybe
those
you can
things.
tell me, either one of you, whether you would agree with the following formulation. Just a single particle in space, classically, we would say, well, it has a location, it has a velocity. And now in quantum mechanics, we would say if you observe it, you can observe a location with a certain probability given to you by the Born rule. You could try to observe the velocity and you would get a measurement outcome for that. But when you're not observing it, we should not attach to it anything called its position or its velocity in a simple way.
Yeah, I think that's a fair statement. I
think
think
so.
what happened, so when you have a revolution in physics, a new theory that really throws things overboard that we had before, it very often happens that people don't take it completely seriously. And that's usually a mistake. Even Einstein didn't take general relativity completely seriously because it predicted the universe would expand or contract.
We're too
And so he
timid in
tried
some
to,
sense.
yeah, then we get too timid. And that's really remarkable because you could not have been a very timid person to discover that theory in the first place. But even, that was so crazy that, he tried to desperately dial some extra dial to make that go away. And in quantum mechanics, I think it was very confusing to people that we could not speak of a definite position or velocity of a particle in general. And we were very sort of tied to those notions from our own intuition and experience in a effectively classical world. And so people, again, messed with the theory and added an extra rule that had to do with like what happens when you make a measurement or an observation. And that was a terrible, terrible idea because it introduced notions into the theory that were ill-defined, and it made the theory more complicated by having two different rules for time evolution. If the unspecified observer doesn't do anything, there's one rule for what happens, and if you make a measurement, then there's another rule for what happens, which isn't even deterministic. And we've come, I think, a long way since then in recognizing that that was unnecessary, and that the theory is easily powerful enough to deal with what we do in measurements without having to introduce these extra concepts that are actually ill-defined, and you'd never know which of these two rules to apply anyway. It's only, I think, when we put this together with an attempt to describe cosmology and the universe as a whole that this problem comes back to haunt us. Because the way that we resolved the problem was by saying, well, in practice, a measurement is anything where you start losing information about the system in some direction that you don't keep track of. It doesn't have to be done by a conscious observer. It could be done by any matter system. But once you start about the universe, you're talking about the universe, you're by definition talking about everything and not excluding anything. And
Nothing is lost.
it's that exclusion of some part of the system that gave us an intrinsic explanation of what a measurement is in quantum mechanics. And it gave us in particular one that applies to all observations that are made in practice by humans, and so it was satisfactory and complete as far as that was concerned. But when we try to describe the universe as a whole, it's unclear how to define this part of the universe that we're suddenly not supposed to care about.
And we're struggling in some sense to put together general relativity, curved space-time, et cetera, with the rules of quantum mechanics.
Yeah, but
right?
those issues are not directly here. Here it's like, you thought that the terrible separation between, I kind of in some sense agree, so it's a good word, but it was a very useful one. And early on, early history of the development of quantum mechanics, that was very useful because we didn't have to talk about it. And it was not obvious that we could do this. Okay, this is something you separated your measurement. But now in cosmology, as I kind of mentioned, if the cosmology means to describe everything, whatever that means, including observers and everything. Okay?
Right.
Observer in this case, it need not be human or something,
Sure.
Of course, as we all agree, but something called classicalized object. Okay? So something we can talk about in the language of Newton's and Galilei and those at least approximately. And those worlds must arise from quantum mechanics in an internal way. But in the early stage of the development of the theory, you just separated that and forget about it. You just come up with the rule of prescription that's called Born rule. We are talking many times. But yes, in cosmology, because we also want to talk about everything, necessarily this issue was back. That is not a priori result of gravity, a priori. Probably the deep down it may be related. But this is back because it's a cosmology.
In fact, in the bad old days of the early days of quantum mechanics, there was what was called the Heisenberg cut.
Yeah.
Where there was the classical world where you and I live,
Yes.
and there's the quantum mechanical system, and there was a cut in between them.
Yeah.
And what you're saying is that if your object of study is the universe as a whole, there's nowhere to cut it. It's the whole universe.
And old days, this is also a bit related with the technical development in some sense. In old days, you may be able to say that the cut is actually there.
Right.
because electrons will interfere probabilistically, something completely quantum mechanical. But we don't seem to interfere. Actually, we currently probably believe interfere, but it's a very small probability. That's why we just don't notice. But nowadays, you can do these interference measurement is molecules or gradually bigger and bigger thing. That's a technical advancement.
The whole world is quantum.
Exactly. Really. So we can't say the same thing anymore. Of course, a lot of physicists didn't believe from the beginning this Heisenberg cut. Right. Yeah. But the technological advancement is also helping us to be convinced more that that's not the way. Yeah. Then you really are forced to think about quantum mechanics for whole. It's a big thing.
So when we try to put it together, if we have this idea that because space-time is curved and can expand, there are horizons and you can't see beyond them. And you also have this quantum mechanical idea that what a person can measure gives you some information, and there's a somewhat vague connection between the underlying ultimate reality and that set of measurements that different people disagree about. What do we get out of that? What is the quantum mechanical way of talking about observers and horizons and so forth?
Yeah.
Well, one question that we can ask when we put together quantum mechanics and what we know about space-time in a reasonably controlled way, even though we don't have a complete theory of it, is when we ask what happens to a black hole that you formed, let's say because some star collapsed. And it turns out, as Hawking showed more than 40 years ago, that this black hole will evaporate. It'll fizzle away the same way that a hot piece of coal that you formed by smashing carbon atoms together will fizzle away. And if you think about this from a quantum mechanical perspective, quite unrealistically, but let's just suppose that you had kept track of all the information about where all these carbon atoms were, or where all the atoms of the star were that formed a black hole. Once the thing fizzles away that formed, you should be able to get that information back by looking extremely carefully at what comes out. There's no loss of information in quantum mechanics. It's a fundamental principle of the theory. And yet, Einstein's theory also tells us that we can fall into a black hole, and there should be nothing special. There's no sign saying event horizon when you cross that point of no return. The same way that there's, you can wade out of quicksand if you're close enough to the outside, but at some point you're not going to outrun the quicksand, and there's no sign there saying, oh, now you've crossed the, Same thing. You're gone, and it's very smooth. It's just sand. You don't even maybe notice that you're sinking. And these two principles, one of how space-time is smooth and should be smooth at the horizon of a black hole, and the other that quantum mechanics tells you information comes back out, for rather subtle reasons, are not compatible with each other. They don't play well together. It turns out that if you want the information to come out, there shouldn't just be a big sign at the horizon of the black hole, don't cross. You should be smashing into what's called a firewall, into a hard thing that's kind of like the end of space-time. And that's exciting to us. The argument for it is rather subtle, and I would say that people are still perhaps trying to poke holes into it and see if there is something that's wrong with it. I don't think there's anything wrong with the argument. It's a very powerful argument, very robust, and it tells you that of these two pillars on which physics now rests, quantum mechanics and Einstein's theory of relativity, we knew they had to give way to some larger structure. We knew they didn't fit together. But we thought that it's like on the map where the dragons live. We thought the dragons lived much further away. The dragons already live at the horizon of a black hole, like the kind of black holes that we see in the universe today, that we see merging, that we see at the center of our galaxy. Those are places where we didn't think quantum gravity was going to be important. And yet we see the two fundamental principles of those two pillars on which they stand. Information must be preserved and space-time must be smooth if there's no matter around. We see those come into a sharp conflict right at the boundary of a black hole.
So you're saying that plausibly adding a little bit of quantum mechanics to gravity doesn't just tweak it a little bit, but it says that there is no such thing as inside a black hole.
Right. And we thought, okay, if you go inside a black hole and then you fly around for a while, eventually you realize, okay, space is really crunching and I'm hitting a terrible thing called the singularity. That was the horrible death I was alluding to. And now it's more like a fly at a windshield.
Yeah.
Before you even ever get to that point in
Still
a place
horrible.
where space was supposed to be nice and smooth and it was friendly and the sky was blue, and all of a sudden it's over.
Do you believe that's true?
I think that the argument
Bayesian prior, 50%, 80%?
Well, I think that it's correct that you can't have information come out of a black hole and not have a firewall. So you have to make a choice. And both of these options are pretty unpalatable to most people, including myself.
Where do you come down?
About the firewall, not too much I would probably add. He explained the problem pretty well, and I don't completely, I explore the way that you can avoid those things, but I'm not 100% sure, to be honest. There is some certain subtlety to still discuss. But one thing, if I could add, is that about this quantum mechanics and observer and cosmology all, is that we really have to understand this, what observation or observer means, to really make deep fundamental progress in cosmology in the real quantum mechanical world. And the key hint is already what Raphael mentioned, that information is preserved and so on. But the other important ingredient is in quantum mechanics, there is a theorem that complete information, including whole what is called quantum mechanical information, cannot be copied. There is some theorem. I cannot.
No really copying of quantum information.
Exactly. So you can't copy information. But what you're talking about, because we're copying information all the time. Suppose we do an experiment and the result was A. I will tell you that, and you know that the result was A. We shared or copied A. Okay, and then I turn it to Raphael and write down on the paper, and somebody see it. We all share that the result of the experiment was A. That's the information was shared. Why? The theorem says that information cannot be copied. We're copying.
Yeah.
The reason is because this information we copied, it's called classical information, is only tiny part of the whole quantum information. What theorem is telling us is that this whole information cannot be copied whole, but the tiny bit can be copied, and that's the part we copy and share, and we later check what was the experimental result, and can you reproduce the same experimental result, and those are only things, in some sense, making sense to really talk, because otherwise you cannot even reproduce, you cannot even share, and then, so the way this tiny information called amplify, like it's copied, but not whole, because there is a theorem.
Right.
So how this process happens is pretty much key to understand what we are talking about, namely.
So our whole classical world is just like a tiny little bit.
Tiny piece of the whole of these things. And those are the things exactly we're talking as a prediction, because we're comparing. You predict it, and I see it. Okay, now copy the information. But cannot be whole, it's only tiny piece. But then which tiny piece will be meaningful to talk about, and how this tiny piece will show up in a more fundamental, intrinsically quantum thing, those are necessary to define even what observation means, and it will be key to do full cosmology at the fundamental level.
And so what you're both telling me is that after decades of effort, we don't understand either black holes or quantum mechanics.
No, I think that's well, you know, that's the kind of argument that could be advanced against any branch of science at any step in their progress, because you go to the limits
But it's good news
of
we
what
don't
you
understand
can, of
everything.
what you understand,
That's good news.
and you find the places where you don't understand.
Yeah.
And the good news is that I think we've sharpened the problem. I mean, no, you know, a physicist loves a sharp paradox. That's when you can make progress. When you know something has to give.
Yes, that's right.
And simple thing is that we don't understand completely does not mean that we don't understand at all.
Of course.
It's a
We
very
know a
different
lot.
statement.
All
Yeah,
right.
we learned a lot, we came a long way, and then not yet.
And I think it's a very good place to wind up. We don't understand everything, we understand a lot. 100 years from now, we'll make exactly that same statement, but the boundaries will have moved a little
Exactly.
bit, I hope.
Right,
All
right,
right, thank you very much.